Good evening, everyone. Am I audible?
Yes, sir.
Okay. My name is Amit. We are conducting mentoring sessions for GATE physics examination. The targeted one is 2023. This is phase two. We have been discussing special theory of relativity in the past 3 weeks. We had gone through some very basic concepts like space time, the concept of space time invariance, and we built on that, and we did some Lorentz transformations in which we learned how to convert the space and time coordinates between two inertial frames. And then in the last class, in the last session, we saw how to convert the velocity, because if you can convert the space coordinate and the time coordinate, that is, if you can convert x and t, you can also convert velocity, that is dx over dt or delta x over delta t. So we saw that in the last class, and we had begun with a few real time impacts like time dilation and length contraction. Due to the lack of time last time, so we will I'll just resume with time dilation today, and we'll also visit a similar concept, which is the length contraction. These two effects we see due to the relativity. In this case, we are restricting ourselves to special theory of relativity. We'll wait for a couple more minutes, because usually I'll begin around 7:04. In the meantime, I'm sharing my email ID. If you see in your chat box, you can see my email ID, which is learnwithamitbansal@gmail.com, as well as the link for the YouTube channel. Why I'm sharing the link? Because in the first phase, I had discussed in the live sessions about electronics part. So we started from current and voltage sources, and then we digital electronics, semiconductor physics, BJT, some FETs, op amps, digital electronics. So if you want to go through, and I covered all the questions of electronics in gate physics from, I think, 2022 up to 2012. So I didn't miss even one single question. If you are interested, you can go through those videos. And even for the special theory of relativity, I whatever session I conduct here, I record it and upload it on this channel. So
Excuse me, sir.
yeah, Harish, go ahead.
Would you like to introduce yourself?
Okay.
Because I am joining first time.
Okay, good. So my name is Amit Bansal. Okay, I am a fourth year PhD student at Indian Institute of Science, Bengaluru. Uh, I'm a scholar in the Department of Center for Nanoscience and Engineering, which is in ISC Bangalore. My work is typically includes gallium nitride devices. So gallium nitride is a semiconductor. You must be familiar with semiconductors are. Gallium nitride is one of the semiconductors. So I fabricate my devices on that gallium nitride material, and I measure its electrical properties. So that's my work. And here I am in the capacity as a mentor for GATE physics. So GATE every year conducts an exam in usually February, or in the first 2 weeks of February or last week of January, something like that. So NPTEL, which is a platform which records the videos of professors in IITs, ISER, and so on. They upload their videos, but this time NPTEL thought that we should also help some students who have like doubts, or they want some concept clearing. And this is a way that each of the scholar for different subjects like electrical engineering, mechanical engineering, chemistry, physics, we just go on weekly sessions are conducted. These are mentoring sessions where the scholars like me are supposed to primarily solve questions of previous years of their respective fields, as well as talk about relevant concepts. And in the meantime, whatever doubts appear, whatever clarifications you may have, so we try to sort that out. So that is the whole summary. Is it clear now,
Okay,
Harish?
sir. What was your get rank?
I don't recall actually, but I hope
Can
I.
you tell range? Your is what range? Your rank range, like 100, between 100 200, like this.
I uh, I'm forgetting, because I'm confusing with the Net rank. I'm sorry, I cannot recall right now. It was below 100, that's for sure. So yeah, that's if that's. But
Sir,
the gate rank is not. I believe gate rank is not relevant. To be honest, for admissions it's relevant. But when I'm sitting here, so I'm supposed to, even if my gate rank were like 1 or 1000, if I'm sitting here and taking these sessions, then just assume that all the scholars which are sitting on this side have just passed through some basic checks that have happened. So yeah, that's it. Yeah, go ahead, Harish.
sir, we have also Telegram group for
Okay, but I'm sorry, I'm not on Telegram. This is a mentoring session. If you have any doubts, if you have any comments, you can write it to my. I've shared my email ID, so we can connect there. But this is a mentoring session, so I'll stick to that. So whatever extra things that you want to talk about, you can write to me, or you can stick around after 8 p.m. and we can talk even on this call. Is it fine?
Okay, okay, sir. Thank you.
Okay, good.
Thank you.
So it's 7:06. Now let's begin. Let me share my screen now. Okay, just hold on a second. Hmm. Um, is my screen visible?
Yes, sir.
Okay. So as I told you, this is now currently we are in week 4 of phase 2. Today is December 18. My name is Amit. We are doing live sessions by NPTEL for physics. Right, so just a very quick review of special theory of relativity. We talked about what relativity, it means relations between space and time. Space we denote by 3 coordinates x, y, and z, and time we denote by t. So typically what I represent is like this: x, y, z, semicolon t. So this is my nomenclature that I have been following. What's special about it? We neglect gravity, because gravity also introduces a relativity, so to speak. So we are neglecting gravity here, hence this is a special theory of relativity. And these are the twin concepts that we had talked about. The first one was that laws of physics will remain invariant in all inertial frames. So what laws of physics, like conservation of momentum, conservation of charge, conservation of energy, they'll remain invariant, means they will not change. These laws will still remain valid. And what are inertial frames? Inertial frames are those frame of reference with zero acceleration. That is, the velocity has to be constant, like 2 meters per second or 0.5 c meters per second, right? Or at rest. This means velocity is equal to 0. So only those frames we are considering. So if the velocity is a function of time, this is not an inertial frame. So in our case, for inertial frames, velocity should not be a function of time. And the second basic concept in this theory is that speed of light is same for all frames. So in whichever frame you are traveling, speed of light will always be c, that is approximately 3 into 10 to the power 8 meter per second. And we saw that see, these terms keep on appearing over and over again, hence I emphasize, hence again I'm emphasizing them today. So we saw what an inertial frame is, right, which is not accelerating. What is an observer? So you can see in this blue frame, we call this as S frame. This is also sometimes called as rest frame, because this frame will not be moving, or this is called as laboratory frame. Okay, rest frame or laboratory frame. This is the frame S. So here is an observer O sitting at the origin of this frame. So this is an observer which will be observing all the things that are happening here. Similarly, here you have one more frame. We call this S prime frame. And this S prime frame is moving with a velocity v, you can see here, in x direction with respect to frame S. So I repeat, frame S prime, and an observer is sitting again at O here, and we call it at O prime. So S prime frame with observer sitting at its origin is moving at a velocity v. This is a constant, hence inertial, with respect to this rest frame S. This we also call as moving frame. It has different names depending on the question and the context, right? And so what does this observer do? An observer captures an event. So let's say there is an event P here, and it will measure its coordinate as x1, y1, z1, comma t1. Similarly, it can capture another event x2, y2, z2, t2. Note this is how we are now writing the coordinates. Similarly, the same event will happen here, right? This is just the observer is moving, right? The event will same happen here, and hence we call it a p prime. Note that in this frame, moving frame, everything is primed. So it will be x1 primed, y1 primed, z1 primed, so on. Similarly, there will be corresponding to q, there will be an event q prime here, and its coordinates will be x2 prime, y2 prime, and so on, right? So these are called events. P and Q are events, and every event will have a coordinate associated with it. So P and P prime, right? The most critical thing, that's what's linking between P and P prime. That is, what is linking between the x1 y1 z1 t1 and x2 x1 prime y1 prime z1 prime t1 prime is something called space time interval, and it remains invariant across different inertial frames. This means delta s squared, it's a mathematical quantity, if you calculate an s frame, will be equal to the space time interval delta s prime squared in s prime frame. So what is the formula? The formula is this: the delta s squared equal to, this is called the time interval, we call this the time interval, and this is called the space interval, and the total term delta s squared is known as space time interval squared. Okay, just hold on a second. Yeah, Harish, go ahead.
Sir, I am confusing with term.
Sorry, can you repeat yourself?
What is the invariant meaning?
Invariant means it will not change. Like, let's say if I ask you what's your name, you will say
Okay,
Harish.
okay, okay, okay.
Another person 2 years,
Okay.
and assuming you have not changed your name, so another person in this chat asks your name, what is your name, you will reply Harish, right? So name is invariant
Yes.
across the frames, so that's what it means. This
Sir,
mathematical
charge is also invariant.
charge is also invariant, yes, because it follows from a
Yeah,
very
okay.
basic principle that charge can neither be created. That's again for a different, yeah. But in
Right.
this to mathematically, so in the previous slide we saw the twin concepts. So how to express those twin concepts mathematically? Hence this mathematical entity space time interval has been introduced by the physicists. So that's what's happening there. Okay, so moving ahead, you can calculate the space-time interval using this formula, where delta t is t2 minus t1. You see t2, t1 I've already defined. So this is just like a distance which you defined in our normal rectilinear coordinates. This is a counterpart to our typical Newtonian mechanics. So that's that. And the last thing we see is what are transformations. This means how to convert p coordinates to p prime coordinates, or if you are given p prime coordinates, how to convert to p coordinates. And we saw that we can convert them using something called Lorentz transformation. And this is let's assume that this velocity v, you see, these are the two frames, the s frame and the s prime frame. Again, this is called the rest frame. I'll keep on repeating these terms over and over again. This is the rest frame, and if I want to calculate, let's say, whatever the coordinates here, so we know that due to Galilean transformation, simple high school mathematics or physics, you can see time will not change, and x prime coordinate here will be x minus vt. This is what we see. Y and z remain constant because the motion is only in x direction. The counterpart to Galilean transformation in non-relativistic means the velocity v. This frame is moving with a constant velocity v. V is less than c. C is the speed of light. And if I want to introduce the same concept in relativistic world, that is v is approximately equal to c, so it cannot be neglected, then these are the formulae that we have derived them. We saw in the we have not derived them, but we have saw that the how are these formula arrived. These formula arrived based on this, that space time interval remains invariant. And so these just as we can obtain Lorentz, so Lorentz means you can obtain the prime coordinates if non-prime are given, right? You see non-prime are on the right hand side, and you can obtain the prime coordinates. This is called Lorentz transformation. The question might require to find the inverse, that is the prime coordinates are given, so prime coordinates are the known, you see x prime and t prime, and you need to find the non-prime coordinates, that is you need to find the coordinate of some p event here, x1 y1 z1 t1, and you are given the p prime coordinate. So we saw that this also we saw, and we solved a couple of questions in the first week. Similarly, just like you can have I told you that velocity is nothing but ux is nothing but dx over dt, or in a if non-infinitesimal, if we say delta x per delta x, we can obtain as x2 minus x1 over t2 minus t1, and using these formula t1 t2, you place 1 here and you get everything. And we had derived these formula ux, ui and uz. So these are, so here again, these are called the direct transformations, because if you are given non-prime coordinates, you can find the prime velocities. Similarly, you can find out these velocities. These are just the formula that we had talked about, and again we had solved a couple of questions, I think, in second week. And this is the thing that we had talked about last class, that special theory of relativity is not something that remains only on the books, though it looks like that. How are we able to achieve close to speed of light, right? It's not realistic. Yeah, today we do not have the technology to do that, but there are some effects which is still observed. For instance, when space agencies like NASA, JAXA, which is Japan Space Agency, ISRO, Europe Space Agency, they keep on sending probes to faraway planets or their satellites, moons. So we do see some effects, although it's in microseconds or milliseconds, but we do see the impact of. So these are the effects that I'm talking about. The time dilation. This is a very realistic phenomena that even the astronauts observe. But I told you the scale is microseconds, so you can even neglect it, and we do neglect it, right? So we'll see these effects one by one. So first, let's talk about time dilation. So there are few terms, and I need you to just be careful. These are the definitions that I will keep using over and over again, and these are the definitions that you must remember, because these terms will keep appearing over and over again. So there is a term called proper time. So proper time is any time if it's measured in object's frame. So here is an object. This is, you can say, the S prime frame, right? So this is the S prime frame, and here is our observer O prime, and it is observing that, let's say let's say there's a ball here and it's striking here, or a photon is ejected from here and it's coming back. So this is measuring the time, how much time it takes the photon to cover this distance, okay? And let's say this length is L, right? And it will simply measure the time. So it will measure the time as, since we are in prime, I'm calling is T prime, it will measure at 2L by C, because length traveled this from this to L and coming back is also L, so 2L by C. So this observer O prime will say that a photon takes 2L by C. These are mirrors, two mirrors, you can say, okay? So this observer will say that I am measuring 2L by C. Remember, this observer is in an inertial frame, moving at a velocity v with respect to this stationary frame. This is our rest frame, right? But here is an observer on the ground. So this is the rest frame, and this is the observer O. So it's standing on ground, on Earth, let's say. So what's happening? This observer will also observe the same motion, but it will see that a photon will not go in vertical direction. It will also translate. Why? Because this mirror itself is moving at a speed v, correct? So this observer will not measure it will measure an extended time, right? So it will measure slightly longer time, and this concept is known as time dilation. Again, coming back to terms, this T prime that this observer measured is called proper time. Why proper? Proper here means the time which you measure in your own frame. So here object is sitting in this cart which is moving at a speed v. So whatever time is measured in this frame is called proper time. Similarly, this length L is called proper length, because this observer measuring that this length is L. So remember, proper is when you measure anything in your own time frame. What is the observed time? So our observer is here, O, which is a rest observer, and whatever time this observer observes, which will be T, this is called the observed time, and it is measured in, naturally, as the name suggests, in observer's frame. So I repeat, proper time is measured in the object's frame. In this case, object is moving at a velocity v in the right direction. Observed time is measured, which is T here, is measured in observer's frame, and our observer here is standing on Earth at rest. So these are the definition.
Yeah. Sir, proper length किसमें measure करेंगे? Object frame में क्या?
Yes, if anything is proper, if anything is set proper, this means you are measuring in that object's frame. So here the object was these two mirrors and a photon, right? So we are in their frame. Yeah. And so very soon we'll see another term, proper length. So proper length is again measured in object's frame. That's why I'm telling you, whenever you hear the word proper, this means you are in that object's frame. As simple as that. So now let's try to just calculate these. We can this is mathematical calculation. So this is L, correct? This will remain the same, because movement is in x direction. So y direction length will not change. Remember, y prime was equal to y in Lorentz transformation if the movement was in x direction. Remember that. So this will not change. So this will remain L, and this will naturally be v t prime by 2. So this length will be vt prime by 2, and total length will be vt prime by 2. So this is, I'm just drawing this half. This will be L. So this is the distance that a photon will need to travel, right? So essentially what I'm saying is that you can calculate this time, and this time will naturally be more than, so you can see that this is the half journey, so we call it ct by 2. So you can see that ct by 2 will be equal to square root of L square plus vt prime by 2 whole square. This is a mathematical expression, but I give you the idea. So whatever time is being measured here, the time measured by this observed time by this observer O on Earth, it will be more, because the photon has to travel a longer distance. The speed of photon will not change. Speed of photon will remain c. We saw in the theory itself. This is one of the second postulates of special theory of relativity. So this thing, when the same, because see, photon is bouncing from mirror, that is true, both the observers saying that, but the time measured by both the observers is different, and this is called time dilation. So here dilation, okay, the literal word dilation in English means expanded or increased. So what's happening is that the time measured by this observer, which we denote by t, will be more than time observed by this observer, the object frame observer. This concept is known as time dilation, because time has now increased, although both are capturing the same event. Now, this was in very simplistic terms, right? And the same concept I'll try to explain now using the frames that we had talked about. Okay, so as this was the frame S, this is the rest frame or the lab frame that we call, and whatever time we measure here is called the observed time, and we don't know this time, so this is an unknown for us. We want to calculate this, right? What we do know, we know that proper time is measured in object's frame. So we saw the object was something like this in this case, right? We saw this. It can be any object, it doesn't matter. That was just an example, right? So this is the object frame, and proper time is measured, as you talked about, measured in object's frame. So whatever time you are measuring here, so for instance, let's say this is event P when it's leaving, right? So it will be, let's say, x1 y1 z, x1 prime y1 prime z1 prime comma t1 prime. Similarly, the event Q, when the photon returns to this bottom slab, it will be x2 prime y2 prime z2 prime and t2 prime. Note that x1 y1 and z1 will be the same. These both will be the same. Why? Because this mirror is not moving, right? This mirror is stationary in this frame, in this S prime frame. Hence these are called co-local events. So what do you mean by co-local events? When their x, y, z coordinates are the same. X, y, z. So x1 y1 z1 primed is equal to x2 y2 z2 prime. This is the definition of co-local events. So I can denote this as delta x prime, which is x2 prime minus x1 prime, is equal to this is the definition of co-local events. Note that I am ignoring y and z because the movement is only in x direction. So y and z will not play any role. So co-local definition is this, and the time observed was this. This is the proper time, t prime, t2 prime minus t1 prime. This is t prime. Now we need to know this. So how do we calculate non-prime form prime entities? Simple. We use inverse Lorentz transformation. So what I need to do, I need to calculate t2 in terms of t2 prime. So I'll do that. So I'll write gamma t2 prime plus vx2 prime over c square. I have just put 2 here, okay? And you get this minus t1, it will be minus gamma t1. So I put 1 everyone here, t1 prime plus vx1 prime over c squared. Very simple. So if you see, it will be gamma t2 prime minus t1 prime. So I've just calculated the first 2 terms from this, and plus gamma v by c square x2 prime minus x1 prime, and we know that x2 prime minus x1 prime equal to 0. That's how we define the proper time. Okay, so this term will be 0, so this will come out to be gamma t2 prime minus t1 prime, and you will get t equal to gamma times t2 prime minus t1 prime is nothing but t prime, is t prime. And we know that gamma is always a quantity greater than 1, right? So you can put any value of v. Let's say v equal to 0.8c. If you put this value here, so it will come out to be 0.6. This will come out to be 5 by 3. Gamma will come out to be 5 by 3, corresponding to this. So gamma will always be greater than 1. Hence, observed time will always be greater than proper time. Will always be greater than proper time. And this concept, when the observed time is greater than proper time, is referred as time dilation, and what we are seeing here. Right. So I'll pause a bit for a moment here and just let you collect your thoughts. If you have any doubts, you can ask me. Otherwise, I have a very simple problem associated with this, and we'll go ahead with that. So I'll pause for a minute, and if there are any comments, any questions, please go ahead.
सर पिछली स्लाइड दिखा ना.
This one?
इससे भी पीछे.
Yeah.
Okay. Next.
I'll be uploading these on the YouTube channel. So if you want to refer them, you can go through the video there. Okay. Right.
Okay, sir.
So what we'll do now, we'll solve this problem. This is a GATE 2014 problem, and it's given that half-life of an elementary particle. So elementary particle may be like a neutrino or a proton or any other particle. There are so many particles, right? With moving with speed 0.9 c in laboratory frame. So with respect to laboratory frame, this particle is moving at 0.9 c, and half-life is given as 5 into 10 to the power 8 minus 8 second. We need to find the proper half-life. Note, the term proper means we need to go into this particle's frame, right? This means we need to find t prime, and this is the t that is given to us. This is t equal to 5 into 10 to the power minus 8, and speed is also given. We'll solve this problem, and c is also given. We'll try to find this, but first there are some pre-checks that we do. That are all the frames inertial? So first frame is given laboratory frame. We know lab frames is inertial, so yes, first frame is true. So frame 1 is inertial. What about frame 2? Frame 2 is this particle's frame. So question is silent about whether it's inertial or not. We'll assume it to be inertial. So if nothing is given, you assume it to be inertial, right? What is the speed of the particle frame, the moving frame? The speed is given as v equal to 0.9 c, and this is inertial. It's a constant speed, right? It's an inertial. Yeah, so yeah, it was given that particle was in an inertial frame. And what is the direction? No direction is given. We'll assume that it's the x direction, positive x direction, right? How many dimensions, like x, y, z, how many are there? Nothing is given. So our problem can simply be fixed if we take the direction of motion to be the x direction, right? In I think second week we saw a problem in which there was x and y directions both, but in this case there's only one direction, right? So this was the problem that was given to us. This is the lab frame, and this is the particle frame. So particle is moving at 0.9 c in this positive x direction, and t has been given to us as 5 into 10 to the power minus 8. What are the units? Seconds. All right. And simply we can apply the time dilation formula. There's nothing to do in this question. Just note that it talks about half-life. So half-life is in seconds or nanoseconds, milliseconds, but it's in seconds. So we can treat it as time. So that's the whole point here. We treat it as time. So we can simply apply time dilation formula. So we'll say t equal to gamma t prime, and we need to find the t prime here, right? Proper half-life. Proper half-life means t prime, proper half-life. Okay, so t prime will be nothing but t by gamma. T we know, we need to find gamma, so I'll find gamma here. Gamma is 1 over v square over c square. This will be 1 minus, the value of v is 0.9 c squared over c squared, so this will be 1 minus 0.81. Now I have to get my calculator. So this will be 1 minus 0.81 is 0.19. So this will be 1 minus root 0.19. So this is coming out to be around 2.29, but I'm rounding off, let's say 2.29. Okay, I'll put this value here. Okay, so this will be 5 into 10 to the power minus 8 over 2.294. So this 5 divided by 2.294 will be 2.180, 10 to the power minus 8 seconds. So this is the proper half-life, this is L, sorry. So we calculated it to be 2.18, or what was 2.18? Yeah, so 2.18, 10 to the power minus 8 seconds. It's straightforward problem. where t prime was t was given to us, and we need to find the t prime for an elementary particle. So this is t, and we simply applied the formula of time dilation. One frame was lap frame and the other was the particle frame. So this is all about time dilation. Now we'll move to a okay, I'll pause again here. If you have any comments or doubts, you can ask me. Very straightforward question. There's nothing fancy happening here. I just spent some time explaining why it's called dilation. Dilation means expansion. So in rest frame, time measured will always be more than the object's frame. So that was the whole concept here. Okay.
Sir, would you please go 2 slides back?
2 slides back. 2 slides. Will this one?
No, before this one.
This one?
Sir, here, how are we getting this C delta T term?
Okay. So okay, these are distances. Okay, so just focus on this left half, let's say this portion. All right, so I talked about this distance is L, so I'll write as L here, right? And this distance is whatever this this cart is moving in the right direction, so that will be, this distance will be V times T prime by 2, where T prime we defined as 2L by C. Okay, now you note that this is the units of distance, right? Nanometers, meters, whatever. Again, this is distance. So a photon will be traveling at the speed of light. We know that a photon will always travel at the speed of light, hence this term C, and delta t is the time taken for it to reach from here to here, hence this C delta t comes, right? Distance equal to speed times speed into time. What's that? V into t. Yeah, distance equal to wind, so it's that. This is a Pythagoras that this is 90 degrees. Okay.
So, sir, I was wondering whether this will also apply when our velocities are not comparable to C.
Yes, correct. This will apply. This will always apply. So when your velocity v is not comparable to c, you see this base will be very thin. So this triangle will then look something like this. And when v is less than c, then this hypotenuse will merge with the vertical line, and you will have non-relativistic regime in which we are all living right now. You're correct. But this is
I think she wants to say that if it is not a photon, then what will it come C into delta t?
So delta t is the time that this observer has a clock in her hand. Okay, there's a clock in her hand. So she is measuring.
No, sir. If the thing in the box is not a photon, it will not be C.
Correct.
Means
correct.
It will not travel with speed of light.
Correct. You are correct. The thing is, I am explaining. See why I took it as speed of light, because it will remain invariant. So when I'm establishing a concept, so first I established the concept that time will not be the same. The whole objective of this slide was to tell you that, if you remember, I was saying that t will be greater than t prime. So that is my whole objective for this slide. How much times is it greater? That mathematics we did in the next slide here. So in this slide, the whole objective was just to get this message across that t, the observed time, will indeed be greater than the t prime. How much will it be greater? We saw in the next slide. And you see in the question that we solved, the particle there was moving at 0.9 c. It was not even moving at c. But we still applied this formula. How could we apply this formula? Because of the fact that there are some expressions involved. And the way we are defining what's the proper time and what is the observed time. So based on those definitions, we can obtain them. Here I was just trying to get this message across that t will be greater than t prime. By how much will it be greater? We saw in the formula that it's greater by a fraction of gamma. Okay, it will be greater, and that's the whole objective of this slide. How much it will be greater, that we obtained mathematically in the next slide.
So, sir, it could be possible that even in the in the ordinary regime also, we get a triangle that is finite in size and still we observe time dilation.
Yes. So first of all, I'm ignoring gravity here, because that will go into general theory of relativity. We are not concerned about that here. In special theory of relativity, in order for the special theory of relativity to have considerable impact, the velocity v, this velocity v, has to be comparable to c. So in our lives, I think the maximum speeds which at least I have encountered is the speed of electrons in lattice that we can see, and that is of the order of 10 to the power 5 meter per second. Okay, this is still 3 orders lower than the speed of light. So even those will not, the fastest moving electrons, or maybe 10 to the power 6 meter per second, even those will not experience the relativistic effect. You are correct. In that's what I'm saying. This base will keep on getting shortening and shortening when we go into non-relativistic regime, right? And in the purely non-relativistic regime, which we are sitting in right now, this is completely, this hypotenuse and this perpendicular, they merge into each other. We cannot tell the difference. We cannot realistically tell the difference. So that happens. That is true. You are correct. But this base is so small that mathematically and even for real things, we have to ignore that. It's of no consequence in real life or even for the sake of solving problems. It only becomes considerable only when we approach the speed of light, like 0.1 times speed of light, 0.05 times speed of light. Only in these regimes then this effect will in a very small measure will come into picture. But it is there even in non-relativistic regimes. It's negligible. It's like 10 to the power minus 3, minus 4, minus 6 orders less, which is negligible. For instance, if you are measuring a time 1 second, maybe you will get 1 second, 1 nanosecond. 1 nanosecond can easily be ignored in terms of 1 seconds. That's the idea. Okay?
Okay, sir.
Okay, good. This was time dilation. A similar concept is length contraction, right? Again, this is the lab frame or the rest frame. And you can see here we have the observed length here. As this suggests, it's measured in observer's frame. The keyword here is simultaneously, means, so let's say this is an object here. And its one end is P, the other end is Q. And its coordinates are x1, y1, z1, t1. Similarly, its coordinates are x2, y2, z2, and t2. Simultaneously means we are measuring the length at the same time. This means t1 equal to t2. So you can see, and delta t would be 0 accordingly. Yeah, Arun, go ahead. Arun Karthikeyan, if you can hear me. Yeah.
Hello, sir. Am I audible?
Yeah, go ahead. Loud and clear.
I'm sorry to interrupt, sir. I just have one question. Do we have any practice or mock test for physics and NPTL?
I don't think so. It's up yet. For some other exams, it is there, but for physics, I just saw the website.
It's only there for engineering subjects, like
Yes,
4
I
subjects
know,
for
I
in
know.
engineering. It's
Yeah.
for physics, it's not there. So I wanted to confirm whether it's there.
No, I don't think it's up yet, because the problem is it's also a thing of volumes, unfortunately, and the people appearing in engineering disciplines are manifold as compared to the physics disciplines, right?
Okay.
So since this is the very first year that we are trying, so this is not up yet. So first, because it's easy to roll out for engineering because there's much more manpower and there's much more demand. So once we stabilize that, I'll pass on this feedback. But sorry, we don't have anything mock test as of now.
Okay. Sorry, sir. Sorry to interrupt. You
It's
can
cool.
continue.
I'm here for that purpose only. Yeah.
Yeah.
So observed length, we'll observe the length between P and Q, and the length will naturally be x2 minus x1. Again, we are ignoring y and z. It's for all practical purposes, you can ignore them. For general, that's for general thing, right? So what is the proper length? As I'm again emphasizing, proper means you are in object's frame. So this object, let's say this is a rod, okay, PQ rod. This rod will also be here. This rod will now be called P prime Q prime, right? So this rod will be here again, and this is again a second frame, S prime frame. Note that this rod can itself be moving, but here I'm taking it to be stationary. Okay, this rod can itself be moving with respect to these frames, but for now I'm ignoring it, right? So proper length will be what? L prime equal to x2 prime minus x1 prime, right? And how do we relate L and L prime? Again, we use the Lorentz transformation. So if you put x2 prime here, it will be gamma x2 minus gamma t1, sorry, minus v t1, my bad, minus gamma, sorry, this is t2, x1 minus v t1. This will be gamma x2 minus x1 minus v gamma t2 minus t1, and since this t2 minus t1 equal to 0, this will be gamma x2 minus x1. This is nothing but gamma L. So I get L prime equal to gamma L. Note, gamma will always be greater than 1. Alternately, I can see that L equal to L prime over gamma. Again, the observed length will be smaller than the actual length, the proper length, by a factor of gamma. Time was larger, remember, time was gamma t prime. So observer will always measure a larger time but a smaller length. And this concept, because the observer is measuring a length, a distance smaller than the proper length, it's contracted. It's contracted as compared to the proper length. Hence, this phenomena is called length contraction. This is not readily observed. Time dilation we can still, to some extent, we have been able to measure in nanoseconds or microseconds. This is much more difficult to measure because you need to have an object, and to calculate distance in traveling at higher speeds is difficult. We have not, and higher gravity, so we have not been able to achieve that. But still, it is there. This effect is there, and this is called length contraction. And this is a problem related to the same concept. A rod of proper length L0, this is 2012 paper. Rod of proper length, not proper. This means this length must have been measured in the frame of the object itself. This rod is oriented parallel to x-axis, so this helps in defining the dimensions, and moves with speed 2c/3 along the x-axis in S frame. So there must be some S frame, and this rod is sitting here. It's not sitting here actually, it's moving ux. The object's velocity is u and it's moving in x direction, hence ux at 2c/3, and I'm assuming it's moving in positive x direction. This is our S frame, and we know its length is L0. Okay, its length is L, this proper length is not in this frame, not in S frame. Its proper length is L0, so I should not write this here. Okay, there is some other arbitrary frame in which its length is L0, proper length, right? Now the observer is also moving along the x-axis. Now there is an observer, right? There is an observer which is moving along the x-axis with speed c/2. So there is an observer. This observer is moving at a speed c/2 along the x-axis with respect to S frame. We call this S frame S prime, and our observer is sitting somewhere here. So this is our observer's frame. This is our rest frame. Rest frame, observer frame. Again, this observer will see this rod. Let's assume the coordinates, end coordinates are p and q. So this fellow will see this p prime and q prime, and again it will see some speed ux prime. Note, everything is primed, very simple. I'm just drawn the diagram. Now the question is length of rod as measured by observer is. So we need to find L prime here in this frame, and we know that proper length is L0, right? So just a precheck. Yeah, go ahead.
सर
Yeah,
सर अभी प्रॉपर लेंथ तो दे रखी है L0. प्रॉपर लेंथ तो हमारे पास ऑलरेडी है L0.
yes, the proper length is there. Go ahead then.
L0 ठीक है. तो आप यहाँ पे S प्राइम प्राइम भी निकाल रहे हो.
Okay, S prime
L
frame.
prime.
S prime is the, see, we need to find the length what this observer is seeing. So if you try to, if you want to measure any quantity, can you, someone is unmuted, can you please mute yourself? It's creating a, it might create disturbance for others. Yeah, so we need to find what this observer is, what length this observer measures. Hence, just to apply the formula, if you can do it orally, it's fine. I am a person who needs to draw the diagram, so this is my approach, right? If you're free, if you can, because some people I know who can just solve this like in the mind, they can draw the pictures. I cannot. I have to draw this, I have to label S prime, S double prime, everything, and then only I'll be able to solve. So that's what I'm doing. O prime, we need to go into this observer's frame and measure the length. Hence I have drawn this S prime frame. So we now need to step into S prime frame and travel with our good fellow O prime and measure the velocity and the length and everything, right? Note that this is the velocity. The rod is also moving, right? Rod is not stationary, and this L0 is measured when the rod is, when you're moving in rod's frame. You're not moving in rod's frame. See, rod's velocity is 2c/3, but frame's observer's velocity is c/2. So these are two different things. If this were 2c/3, then the answer would be L0 simply, but it's not 2c/3, it's a different velocity. So this observer is moving at a different speed with respect to S. So you can assume that this O prime is here. This is O prime. And O prime is moving at a velocity c by 2. So this is in S frame. So an observer O is sitting here. So observer O, what does it say? It says that there is a rod PQ. It's moving at a speed 2c by 3 in positive x direction. O also says, I have a friend O prime. This O prime is moving away from me in x-axis at c by 2. And now I've drawn this picture from O prime's perspective. This clarifies things. This makes it simpler to understand for me, and I hope for others too. Right. So what are the inertial frames? Are the frames inertial? Yes, the frames are inertial. First frame is at rest. Very good.
सर
Yeah.
सर यहाँ पे ये जो ओ ओ जो पॉइंट ओ पे है उसको जो रोड की स्पीड है वो 2c/3 दिखा रहा है ना,
Yes.
और उसकी लेंथ l नॉट दिखा रहा है.
No. This L naught was measured in some another frame S prime prime. If S prime prime were moving 2c by 3, then the length of rod measured P double prime Q double prime, this length is L naught. Here it's not L naught. Here it's L naught in this another frame S double prime. No, that's why I tell you proper length is measured when you are in that object's frame. Here the object is moving, object is not at rest. In this S double frame which is moving at 2c by 3 with respect to S, here the length will be L naught, not here. Here it will be something else. It will not be L naught here. Okay, so I understand the confusion why it might have. I should have made this clear before, but this is a different frame S double prime where the length measured is L naught. The length here is not L naught. We are concerned about this frame here. So since I've introduced S double prime, so S prime, is it inertial? Yes, it's moving at a constant velocity c by 2. Is S double prime inertial? Yes, S double prime is moving at a constant velocity 2c by 3. All these three frames are inertial, right? Let's talk about moving frames, the speed and direction. So S prime speed is c by 2 and direction, it's given in the question, x-axis. So x, very good, or I cap, whatever you want to say. Similarly, S double prime is moving at 2c by 3, again in I cap. I've assumed it's in I cap. Okay. Number of dimensions, see the question directly refers only x-axis. So we'll only consider one dimension, that is x-axis. So you notice everything is in the x, oriented along the x direction, all the velocities and everything, right? So this is again a different way of drawing the same diagram. This is S. Here you have PQ, the rod, and it's moving at a velocity of 2c by 3. This is our fellow O prime where it's sitting, and its velocity is c by 2. It's observing this rod P prime Q prime here. This will measure its velocity as ux prime, right? And we know that the length contraction in this frame, what will the length contraction be? So length contraction is this is the observed length, right? So I should actually say it like this. So length contraction would be the length, I'll write this formula again. So length contraction will be observer's length equal to proper length by gamma. What's the proper length? Proper length is given L naught by gamma. Now, and we know gamma is 1 over 1 minus v square over c square. Now this is interesting. What is this velocity v? This velocity v is the relative velocity of object with respect to frame. I repeat, this velocity v relative, is the relative velocity of object. The object here is PQ with respect to frame. In this case, it's ux prime. So we need to find the object of this velocity PQ with respect to our observer, right? This means we need to find ux prime. And how do we find ux prime? Using this formula. So ux prime would be ux into v. So ux is given 2c by 3 times v. V is c by 2 divided by 1 minus 2c by 3 times c by 2 over c square. So these get cancelled, this gets cancelled. So we'll get c by 3 over, what will it be, 2 by 3. So we'll get as c by 2. Okay, so I get the ux prime as c by 2. Now I'll simply put this fellow here. So if I put this here, 1 minus, so c by 2 will be c square by 4c square. This will be 1 minus 1 by 4. This will be square root of 0.75. So this will be square root of 0.75, right? So this is coming out to be 0.87 L naught. So what I did, I put here, so it will be root 0.75 times L naught, and if you do root 0.75 is 0.87. Okay, so so that's how we sorry, my bad. Yeah, so that's how we solve this problem. This problem had two stages. First, we needed to find, this is the formula that we knew already, right? That observer's length equal to proper length by gamma. Proper length was given. We needed to find out gamma. Gamma is 1 over 1 minus v square over c square. What is this velocity v? This velocity v is the object's velocity with respect to observer's velocity. This means the symbols that I've used in the previous classes, this means ux prime. But ux prime was not given, ux was given. Hence we obtained ux prime using this formula and we put the values here. Yeah, go ahead.
ये आपने जो अभी लेंथ निकाली है वो एस प्राइम फ्रेम में निकाली है या एस फ्रेम
S prime frame, S prime, in S prime frame. Observer is here. That's why, see, that's why ux prime, right? So everything.
Sir, can you repeat this question again?
Okay.
Thank you, sir.
So okay, I'll start from here. A rod, PQ rod is given whose proper length is L naught. It's moving at 2c by 3 in this S frame. And this S frame also says there is an observer O prime. It's moving at c by 2, right? So now this frame I have drawn with respect to this observer because we are interested in this observer. So this is the observer O prime. Obviously it will be at origin. And this frame is moving at c by 2. This is the S prime frame. And here this observer will again, just like this observer was seeing this rod in S frame, similarly this observer will see this rod. Now the rod has now transformed into P prime Q prime, and the velocity has also turned into ux prime. Now we needed to find the observer's length as per O prime. So we find proper length by gamma. This means L naught by gamma. Gamma is relative velocity of object with respect to observer. So what is our observer here? Observer is O prime. Note, with respect to O prime we need to find. This means we need to find the velocity of this rod, which is ux in prime frame. Hence we need to find ux prime. And this is the formula that we have seen in the velocity transformation exercises. And we simply put it and solved it. So that's that. And yes, so this would be the answer. 0.87 L naught. Yeah. So any comments, any questions about this? This had
Got it.
sorry.
Got it.
Okay. Okay.
सर एक चीज और बता दो आपने जो पिछली क्लासों में स्पेशल थ्योरी ऑफ हेलो
Yeah, go ahead, Harish.
सर पिछली क्लास स्पेशल थ्योरी ऑफ रिलेटिविटी के बारे में कुछ पढ़ाया?
That's what I said. If you have any doubts, I have uploaded the previous sessions on my YouTube channel. I shared that channel in the I'm again sharing my email ID and YouTube channel link. You can go ahead and watch those videos.
Okay, sir, got it.
ठीक है. Right. Other people, any comments you have? Or we move on to the next topic. So next topics will be less painful. We talk about mass, momentum and energy. Again, you can see on your left in the blue you have the rest frame. And the observer is sitting at O. So this what it's doing, and this is a particle, let's say P. And it has coordinates x, y and z and t. This is our notation. And let's say, okay, so now there's a concept of rest mass and relativistic mass. So let's say this particle P is at rest. Then its mass would be m naught. Okay, I repeat, in rest frame, if this object is also at rest, this means its velocity is 0. Ux is 0. I'm ignoring y and z. Or you can assume yz is also 0. So if this particle P has velocity 0, then its mass would be referred to as rest mass, and it would be denoted by the symbol m subscript 0, m naught. This is how we define the rest mass. Similarly, let's say there's an object q here. There's an object q and it's moving with some velocity, let's say v equal to 0.5 c. Then the mass of this object, it will have two masses. First, the rest mass, which will, let's say, be m q naught, mq is the mass, not to denote that's rest mass, and it will have a relativistic mass which will be given by gamma mq naught, right? So there is a, so you can see that the mass changes in non-relativistic mechanics. If an object in, let's say in the high school physics, or maybe in your bachelor's, if a ball was moving at 1 meters per second, and if its mass was 100 grams, and even if this ball, same ball, was moving at 10 meters per second, the mass remained the same, 100 grams and 100 grams. This is not the same relativistic mechanics. The mass also changes provided it's moving at a speed closer to the speed of light. Otherwise gamma will come out to be 1, right? If v is less than c, then gamma approaches 1. You can put in the formula and see that this is rest mass versus relativistic mass. Okay, now once we have the mass, you multiply. So again, this is the particle q, and it's moving in the velocity ux in this in x direction. So what will the momentum? Momentum will be m times u, straightforward, right? Mass times the velocity. What is the mass? Not the rest mass, remember, relativistic mass. So it will be gamma m naught times whatever the velocity here, in this case ux. We'll solve this problem. I'm just introducing the concept, which is very straightforward here, because momentum is mass times velocity, but mass, if it's relativistic, you take this mass rather than the rest mass. A related concept is energy. So mass, so rest energy is m naught c square. You must have heard that E equal to mc square, the famous equivalence, right? So here the energy E naught, the rest energy, will simply be whatever the mass is, okay, m naught times c squared. This will be, and this is what is called the mass energy equivalence, this expression. Similarly, for relativistic energy, this is the expression on the bottom. So it forms changes. So this you can assume it like that, that this is just like, just a second Harish, that you can see that this is the I should not say potential, this is, you can say this is the energy that it will always have, and because the object is moving at some velocity, this means it has non-zero momentum, so this term will get added, right? So we'll keep this, we'll try to see if we can solve some questions today, but this is what's happening, right? So pc whole squared plus E naught squared, this is the relativistic energy. Note that relativistic energy again will always be greater than the rest energy. Similarly, relativistic mass will always be greater than rest mass, because we know gamma is always greater than 1, right? So these are some very simple things which you can keep in mind, because numerically if you solve what is the value of gamma, it's always greater than 1. So relativistic mass will always be greater than rest mass. Similarly, relativistic energy will always be greater than your rest energy. So these are the twin things that we can take away from here, and obviously E naught equal to mc square. And again, if we go ahead and solving this comes out to be mc square, where m is gamma m naught. So it all just really settles very nicely. So again, E would be greater than E naught always. Similarly, m will be greater than m naught always. So this is the, I have just introduced, we do not have much time. Let me see. I'll try to solve one question, and then we can take, so if you have any comments, please on this, please speak. Otherwise we can quickly solve a problem and we can continue in the next session.
Go ahead.
Okay.
Go ahead.
Okay, so 2022, the most recent paper, and a very simple question was asked. So it says that two identical particles of rest mass m naught. Now again, note the word rest mass m naught, and again this naught symbol, approach each other with equal and opposite velocities 0.5 c. So here is my frame, S frame. What I am seeing, that this particle P is moving, let's say in 0.5 c this direction, and its rest mass is m naught. And another object Q is there, it's moving 0.5 c in this direction, again its mass is m naught, right? We need to find total energy of one particle as measured in the rest frame of other. Okay, so we have to go into the frames of one of these particles, right? So I'm going this P's frame, so this is S prime. This means this frame will move at 0.5 c. Note, I'm going in P's frame. You can go is Q's frame, it will not change the answer, just because we are habitual of seeing this direction, that's why I'm doing this. So here I'm in P's frame, so I can say this observer is P here. O prime, the observer which is say, is nothing but P here, only can say P prime because everything is primed. And so P will remain to be at origin, right? But Q will become Q prime, and it will move with a velocity like this, and let me call this velocity as ux prime. So here let's say this is ux, okay? So here, and obviously velocity will become primed, and we'll find the so what we need to do is we need to find the energy of q in this frame. So we need to find eq prime. That's what it says, total energy of one particle. So total energy of q as measured in rest frame of other. So other I have assumed to be p, and this particle I have assumed to be q. So I need to find the energy of q in p's frame. This means prime frame. We need to find this quantity. As always, before solving the problem, we check whether the frames are inertial. So S was rest frame, so S is inertial. S prime is moving at constant velocity 0.5 c. This is also inertial. What is the speed of direction? Speed of S prime, which is the frame of particle, first particle P, this particle, is 0.5 c, and direction I have taken to be positive x. Number of dimensions. Question is silent, and all of our problem can be solved if we take one dimension. So this is one dimension, which in this case I am taking to be x axis. Right. So I just, as I told you, we just need to find the eq prime. So quickly, this is the rest frame, this is the p prime frame. I can say this to be p prime. Okay, and this is moving at a speed of c by 2. This was given, and this particle q, which in this frame becomes q prime. So there were two p and q were here. P was moving at c by 2, q was moving like this as c by 2. Right. So q prime will have ux prime. This is nothing but ux is c by 2, and we need to find eq prime equal to what? And we know the expression for eq is that gamma mq naught c squared. This is what we know. The relativistic energy is gamma times the rest energy. So rest mass is mq naught, c square is a constant, so we just need to find gamma, right? So we just need to find the gamma over here. So how do we find gamma? Gamma is 1 over 1 minus v square over c square. What is this velocity v? This velocity is object's velocity with respect to observer. We are in this frame, remember. So what is the object? Object is q. What is the observer? Observer is p. Or in other words, we need to find ux prime. We need to find the velocity of q, which is in p's frame. This means we need to find ux prime. So I can say this is 1 minus ux prime squared over c squared. What is ux prime? Ux prime you can find here. So ux is given as minus c by 2. Note, negative direction. V is, this velocity v is c by 2, minus c by 2. 1 minus c by 2 into minus c by 2 over c squared. So this will come out to be minus c divided by, sorry, this is plus. So this will come out to be 1 plus 1 by 4. So this will come out to be minus 4c by 5. So minus 0.8c. So I put this value here. This will come out to be minus 0.8c squared over c squared. C squared gets cancelled. 1 minus 0.64, which will be 0.36, and this will come out to be 0.6. So this will coming out to be 5 by 3. Okay. So I put the value of gamma here. Note, gamma is greater than 1. I told you gamma will always be greater than 1 or equal to 1 when v is very close to c. V is less than c. So eq prime, I put this here. This was gamma mq naught c squared. This is 5 by 3 mq naught c squared. This is what we needed to find out. So I'll go again here. I found eq prime equal to 5 by 3 mq naught c squared. Mq naught is nothing but m naught. This was given, two identical particles of rest mass m naught. So this will become 5 by 3 m naught c squared, and this is the energy that was given to us. So eq prime is this, which is equal to alpha m naught c squared. M naught c squared gets cancelled. Alpha will come out to be 5 by 3, which is 1.666. And note, 2 decimal places. Be very careful with this. Okay. 1.66 gets rounded off 2 decimal places to 1.67. If it says 2 decimal places, you have to say 2 decimal places. Let's say if the answer was 2, let's say in some question you come out alpha equal to 2, then you need to write 2.00, not 2. Okay, be very careful. You have to write 2. There's a provision for entering decimal and all in the gate paper when you appear on your screen. So please remember, if say 2 decimal places, then it has to be 2 decimal places. Either round it off like this, or if it's a whole number, then you add another 0. Or let's say the value was 1.6 here. then the answer would be 1.60. This 0 is very important. Okay, I don't think we have much time. Yeah, it's already 8 o'clock. So I'll pause here. I'll go back to this slide. I'll again just summarize this question. So there were two particles that are approaching each other, which we see here, over here, P and Q, and these are the directions. And we needed to find the energy of Q in P's frame. Okay, so we drew another frame, the moving frame, with same velocity as P. So you see this velocity is 0.5 c, and we simply needed to find ux prime, because in energy's formula this gamma term is there, and gamma is nothing but the relative velocity of object, the object's velocity relative to the observer. So we needed to find velocity of Q in P's frame, which is the nomenclature that we are following in the previous sessions, which is ux prime, and hence we just put in the formula, we get the value of gamma, and we just equate and we find the value of alpha. So this was a similar problem, very similar problem, very simple problem, but you don't have time, we'll do it in next class. So I'll pause here. And if you have any comments and questions, please go ahead. Once again, this will be uploaded to YouTube. I'll try to upload it today. Hopefully I'll be able to upload it today. I have some editing to do, but it should be up today, and you can watch it for any, and you can comment there. If you don't feel comfortable commenting, just send me an email. I've already shared my I'll share it again, my email ID and the YouTube channel link. So I've shared it again. Someone asked the previous sessions on special theory of relativity, you can also see on the website itself, on the YouTube channel itself. So yeah, that's that. If any special if you people have any other comments or questions, please go ahead, feel free to ask. And if you want to leave, you are anyways free to leave, but the session from my side is over now. It's open to doubts now, so I can stay as long as you want.
Thank you, sir.
Yeah, welcome. Anyone questions, comments? All right, in the next class we'll continue with the energy, because this is important. This is just a very simple formula, like m equal to gamma m naught, and energy equal to gamma e naught. You just need to calculate gamma, and to calculate gamma you just need the relative velocity. And if you just understand how to draw those frames, that's my approach. So I just draw the frames and everything just falls into place. It becomes very simple. So if no comments, then I'll close this session. Thank you, Amit. You're welcome. Yeah, thank you everyone. See you next week.
Sir?
Yeah, Sejal?
Sir, is girl that you were mentioning, the base of the triangle should tend to 0.
Yeah.
Because I was just trying out that problem. I took some arbitrary length and arbitrary velocities, and the speed was just very ordinary, and I to calculate the time from the other frame, I divided the distance by time in general, and there's no reason, if we just take any arbitrary value, there's no reason that time which is measured from the other frame should tend to be the same as that.
No, time will okay.
Which was
so let me just share my screen again. Okay, where is it? Okay, I hope you're able to see my screen.
Yes, sir.
Okay, so I'll draw the same thing again. Okay, so what we had was something like this. So this photon was traveling from here to here, and this distance was L. Pardon my drawing, these are horizontal, these lines are horizontal. So this distance was L, and this distance was V, which was the distance of the other frame, the spaceship frame, whatever you want to call it. And I call it, let's say, I'm just calling it V. Okay, and so what it did was that, so in this frame, the same photon was traveled from here to here, and let's say I call this time T prime. Why prime? Because we are in prime frame. You know, I denote moving frames as prime. So this time, let's say I call as T prime, small t prime. So what will be this distance? This distance will be Vt prime. Now remember, these are distances that I'm drawing here. So whatever time the photon, so photon took T prime time to come from this mirror to this mirror. Okay. In the same time, this object, this mirror system will have moved Vt prime distance in positive x direction, which I have drawn here. This is the photon, it's hitting here. So this is the event P when the photon leaves this P prime, sorry. This is the same event P here when the photon is about to leave. This is the event P when the photon just strikes the second mirror, and correspondingly this is the Q time. This is the Q prime event, that's its photon striking the mirror. Direct correspondence, right? And what I was saying that since photon will travel with the velocity c, right, and let's say the time travel by photon, time taken by photon to travel this distance is t. Why t? Because we are in rest frame, and the same it was t prime here. So, and you can draw a you can do a right angle here, and I can simply, I'm drawing this right angle triangle here. This is L, this is Vt prime, this is Ct. By Pythagoras theorem, I can say Ct whole squared, hypotenuse square is equal to perpendicular square, which is L squared, plus base squared, which is Vt prime whole squared, right? So now what I'll do is that, yeah, now go ahead, now tell me what approximations you made.
Yes, sir. So firstly, here I assume that we do not have a photon. We simply have a ball which is falling inside a bus. So I assume that the velocity is small v times t, whatever time it takes. And then I divided this whole thing by the velocity for the velocity that would appear to the observer in the other frame. So if here it is say v, for the other frame it would be both in the x and y directions. Earlier it was only in the y direction. Now we'll have some component in the x direction and the y direction. We'll square and
Correct,
we'll
but
take the magnitude.
that won't matter. Y direction will not matter. I'll tell you why. Because we are talking only about the event. Okay, we are only interested, we are not interested in what is the velocity right immediately before the striking. We are only interested at what time it hits. So if it's falling with a velocity so you're saying it's falling with a velocity vy in this frame, it will have a different velocity vy prime in this frame, and hence this times will be different. That's your argument?
Yes sir, exactly.
Okay, so okay, what I'll do is I'll try to solve it, and I'll try to get back to you. Just drop me an email on my email ID so that I can remember. Okay, and we can share it with the class in the next week. Okay, because
I think it should be that because the y component, yes, the y component also, no, yeah, so the y component will not change, only the x component, the v velocity of the frame itself will get added on to the x component.
And so that's how it will not matter, because what I did is, I'll be honest with you, when I before doing a session, I have to read a lot. In fact, in this topic I have to read a lot. So what happens is that I also get confused. Like you see in the last class, I got confused in the time dilation. I had to repeat the time dilation topic all over again today. It's fine, I get confused. It's fine to get confused as long as you're able to make your way. That's why I insist on making the diagrams. S frame, S prime frame, S double prime frame. Whatever approach suits you, but we'll take this out offline. Will not Sejal, just email me, and so I can reply to you. Any other people, if you have any comments, please go ahead.
So just something offside. If we consider a container having a liquid in it, and we move it with the speeds comparable to light, okay. What will happen is that the observer in the rest frame will observe the container to be contracted, okay, and it will have a relativistic mass also, means it will be gamma times m naught something.
Correct.
So if you consider the density of that liquid, then it will be proportional to gamma square times, means it will change fast. So
just 1 second. Density is mass over volume, right? So we are saying that relativistic mass will get amplified by gamma, correct? And the length contracts by gamma, correct? You are correct. The density, it seems like density will be gamma square. Yeah. Hello.
Sir, the density will change by a factor of gamma square.
In x direction. Please note that.
So density will be uniform, no? I think
no. Density can be see, when an entity is uniform in all three directions, we call it isotropic. Okay, it can happen that that an object that some entity is different in x direction and y direction. Okay, it is possible. We see it's not something hypothetical. Okay.
No, sir, I'm talking about normal water
No,
with
I,
pH 7.
I know you're talking about normal water, but it is possible that the density in x direction and y direction are different. That is possible. That's all I'm saying.
Okay.
So density
Yes,
will
sir.
be.
I was just considering that if density is changing by gamma square factor,
Uh-huh.
and if you consider two molecules of water, then consider some hydrogen bonding in M. So, sir, it will change by gamma factor, considering the length contraction.
nahi, so that's the thing. See, density, if I remember correctly, density is a macroscopic entity, right? It's not a microscopic entity. Density, it depends on the total, let's say in a unit, or you can say in a unit cell. So when you're talking about individual molecules or interaction between individual molecules, so I think you have to change your track a bit. So you have to consider those two individual molecules as particles. So you can say the bond length, in this case you're talking about hydrogen bonding or whatever, so that will get contracted accordingly, right? And plus there are few other considerations which are not taking into account here. The first thing is that the energy, is it the bonding energy, is it a factor of velocity? I don't think so. I'm not, I do not know how do the hydrogen bondings work. I'm sorry about that. But there will be different some factors to be considered. But primarily, hydrogen bonding will depend, if it depends only on length in x direction, then it will, since the length is shrinking, so if length is shrinking, I assume half mx square. Okay, yeah, energy is half mx square, right? Half, the kinet, that potential energy of a spring is half kx square, right? So if x is decreasing by a factor of gamma, then energy will increase by a factor of gamma squared. What was your question, by the way, Mandlik?
I was saying that means I don't know up to which extent it's correct, but if density is changing by gamma square factor and lengths are contracting by gamma factor, then the will observe that something is turning into solid before it is means, and its molecular length, intermolecular length is more, but still it's solid.
No. Okay, so now you're talking about phase change. So it can see the phase change. Phase change only happens at some critical temperature. There's if I remember, there's a temperature pressure graph, and there is a line. There's a triple point also, something like that, as far as water is concerned. But here you should not consider the phase change to be more specific. Here what we are, so let's say that even the length is contracting, let's say the length contracts, that doesn't necessarily mean that the liquid will convert to solid. Please understand it. And moreover, if you case the consider of water, so water, ice is less dense than water, right? So in this case, ice intermolecular distance might even be more. So here the water will be pressurized, yes, because the intermolecular length would have contracted. That is true. But changing the phase, I don't think it will be valid here, because it's a function of the phase change is a function of many, of at least of two things: the temperature and the pressure. Okay, so phase change, it will not go under spontaneous phase change as we move this container of water in the at relativistic velocity. So I don't think so. It will be pressurized, that is for sure, but then temperature also plays a role. So I cannot comment on that it will, but temperature it will freeze, but there will be a factor. The intermolecular distance will be shortened, that is for sure. Yeah, correct. It's a good question, actually. This is a good thought experiment. I had never thought about it. In the last class, someone asked a velocity of photon with respect to another photon. That even that we solved in class, real time. But these are very good questions. Yeah.
I only asked it.
No, it's good. It's good. It's only by these questions you are able to understand. You are able to appreciate this. This is not purely theoretical, but we do not observe these effects in real life. You can see a ball traveling at 100 meter per second. You can see, you can hear a supersonic jet traveling over this more than the speed of sound. You can see those things. You can observe those things with your eyes or ears and other sensory organs. But you cannot. As apart from the CERN in Europe, These are very, we do not observe them readily around us, so that's difficult to imagine. This is a good thought experiment actually. It's a very good point that you raised. Thanks, Mandlik. Yeah. uh, if any other comments you have, please go ahead.
सर आप स्लाइड भी अपलोड कर रहे हो क्या? मतलब मुझे यूट्यूब चैनल पे दिखाई नहीं दी स्लाइड पिछली क्लास में.
No YouTube channels. I am Harish. I am uploading only the videos which we discuss here. That's it. There are no slides there. So if you want to see the slides, what I suggest is that you pause the video at some specific times and you just see the slides. That's
Okay.
what I would suggest. I'm not planning to upload the slides as a separate on some separate platform or anything. No. And if I think last I don't know, somebody asked me that whether I plan to upload other questions for other exams. I have no plans right now, but I do notice that there's a jam portal also open for gate NPTEL site. Okay, I'll share the screen right now. I should have shared this earlier, but I forgot. Just hold on a second. I'll try to find that page. Can you see the screen?
Yes, sir.
So there is this
Yes, sir.
jam 23 page. Okay, this, yeah, there is something, but there's not much actually. So there are some lectures if you want to go through. These are the NPTEL lectures. If you want to go through, I mean, it's your choice. I'm just, because I know some people were there in the first class. I asked that whether they want to what's the background. So some people were preparing for jam also, so that's why it might be helpful for those people. Okay, all right. Any other comments or questions? Otherwise we'll close this session. Okay, so yeah, that's all then. Thank you for your patience. Thank you for staying 22 minutes extra. See you next week, where we'll again be talking, and the next week will be less into concepts and more into problem solving, because energy and momentum, this is just a simple formula, m equal to gamma m naught. That's it. There's nothing else to do there. So we'll solve a few problems. We'll approach with different we'll try to solve this question with maybe a couple of approaches, and as again keep the discussion fruitful. Thank you for your time today. Good night. Stay safe.
Thank you, sir.
Sir? Hello?
Yeah, Mandlik, go ahead. Other people, if you want to leave, you can leave. You don't have to stay. I'll be uploading this anyways on the YouTube, so you can watch there. It's your choice. Mandlik, bolo. Go ahead.
Sir, when something is moving, it will have means relativistic energy, no? Means
Yes.
its energy will increase
Yeah.
anyhow.
Yeah.
So can we assume that the water in container will have an increased energy, and it may be getting converted to heat energy?
See, I can only comment that much, that its energy will increase. Okay. Now, once an energy of a system increases, and we also know because remember I told that laws of physics will remain invariant, right? So when the energy of the system has increased, so an energy can neither be created nor be destroyed. Conservation of energy. So that energy which has increased can primarily, it's formed in the form of kinetic energy, because it's moving, right? It's moving, so it's a kinetic energy. Now what can happen, because there is some viscosity, there is some friction between the two consecutive molecules of water, or two different layers of water in this case, there might be some viscosity. I don't know how will viscosity change, and usually if there is viscosity, there is some heat generated, because what I understand is viscosity is nothing but is a manifestation of what we call friction in non-wet world. It's viscosity where the layers are sliding over top of each other. There is some friction involved, so some energy is lost there. That is true, but I cannot comment ki it will be converted into heat energy, and if it's converted, to what extent it's converted. The energy conversions is a completely different phenomena. We don't know. It might happen that some molecules, that rate of evaporation increases, right? It may happen. I don't know actually, but yes, energy will increase. How then this increased energy, where will it go? That's a completely different problem, which you have to approach from a thermodynamic perspective, right? That what is the entropy, will the entropy increase or decrease, and some maybe fluid mechanics concept, because viscosity is involved. Since I'm not since I have very bare minimum knowledge of the fluid mechanics world or the thermodynamic world, so I'll not comment. I'll not say it will increase or decrease or yes or no. That's that. Okay. Hello. Okay. Yeah, I'm done. Okay, thank you. Martlik has left. Now I'll close this session. Thank you for your patience. Thank you for staying along. We'll see you next week. I'll see you next week. Goodbye.